Okay, so hello, I am András Kovács. I'm currently a master's computer science student at the ELTE University, and I'm going to talk a bit about new GHC 8 features, and it's not going to be about all of them. So I'm going to focus on the new features that are most interesting for type level programming and changes to the type system. So first I'm going to talk about the type in type extension, and it's a pretty dramatic change to GHC because it completely changes the core representation. So GHC has a core representation called GHC core, and basically this extension called type in type changes the kind system as implemented in GHC. So in the old GHC we had 4 over levels. So we had terms, and so the usual term language, and we had expressions, lambdas, functions, bindings, type class dictionaries, and things like that. And we also had the type level. And at the type level we had classes, type families, lifted data enabled through data kinds, but we don't have any functions or let bindings or case expressions. So it's a bit less expressive. And at the kind level we had all the lifted kinds, the star which is type, and all the type constructors which are generated by the kind arrow. So we had star to star and star to star to star and so on, but we don't have any functions or any type families or any classes. So it's even weaker than the type level. And there is a little known 4th level, which is called the sort level. And the sort level contains a single value called box. And you can't directly program with it, but if you try to print some pretty complicated kind polymorphic types, sometimes GHC would print you the box. And basically all kinds have sort box. So the sort level is an extremely limited language. You can't really do anything on the sort level. So expressivity decreases when walking up the hierarchy, but it would be eventually much nicer if we had actual dependent typing. And in most dependent type theories we have an infinite ladder of levels, and each level is able to talk about the level beneath, but each level has pretty much the same expressive power. So the type level has all the term level constructs, and the kind level has all the type level constructs, and so on, and you have an infinite hierarchy, and so abstraction does not really stop at any level. And so advantage is no ceiling to abstraction, no multiple languages with different semantics. For example, in current Haskell, the type families act as functions on the type level, but they have very different semantics and very strange and wacky semantics compared to what you would expect from normal functions. And so it's basically a simplification, because you need only one language with one semantics, and you can use it at all levels of abstraction. And also the most common dependent type series have a really large amount of background research, so you can tap into that and get inspiration. So disadvantages. So most of the things that you usually hear about dependent types are basically as disadvantages. So it's basically just myths, because for example, verse type inference. So if you add dependent types, type inference for the same part of the language that you could infer before remains exactly the same. You just get new types and new features and some extra expressive power, but you don't lose the inference that you already had. But you also gain new kinds of inference. For example, when types can depend on terms, you get term inference. So you can basically leave actual parts of your program implicit, and unification can fill parts of your program, not just parts of your types. And there's no phase separation thing, so basically, so if you want phase separation, then you can have it. Because even if you have dependent types, you always have the option to include some kind of phase abstraction or include some kind of mandatory parametricity. So you can have, for example, in GHC, there is the dependent Haskell is under development, and there are detailed plans for it. And for example, dependent Haskell would be dependent, but would have pretty much the same kind of phase separation as the current GHC. So it's not necessary that we lose phase separation. And even if we have no phase separation, it's not necessarily the end of the world. Less erasure, this is actually false because you can have more erasure if you have more static information.
Can you explain what is erasure and phase separation?
Erasure. So phase separation. So phase separation means that there are parts of your program that only present at compile time, and there are parts of your program that are present only at runtime. And with dependent types, it's sometimes necessary to run parts of your program at compile time, and the same parts of your program will be also run at runtime. So this is phase separation and erasure. So erasure is, for example, in current GHC, erasure means that if you have, so the types don't appear at runtime. So for example, if you have a polymorphic identity function, then GHC will generate some code for it, and that code is does not mention the type, and there is no type information present at runtime, because a single code generated for the polymorphic identity function is able to handle all polymorphic data passed to it as input, and there's no need for any runtime type information. That's basically erasure. And if you have dependent types, you are quite often able to analyze your data definitions and at compile time find all the parts that can be erased and all the parts that cannot be erased because there's some kind of actual computational dependency, and you can erase quite a bit more if you can do that than GHC, because in GHC there is a very, very limited set of things that you erase, and it's basically GHC erases all the types and all the kinds from your program, but can't erase anything else. And if you have dependent types, then you can look at your data definitions and find all the things that are not types or kinds, but can be erased anyway. Oh. You're going to be quite slow. So what typing type does? So typing type merges levels 2, 3, and 4 into a single level. So there are no kinds and no sorts. Only terms and types exist now. And so what classifies types? So we don't have any kinds, but types now classify themselves. So I can illustrate it. For example, what's the kind of star? The kind of star is star itself. So star, this is what we mean by type in type, because star, which we should call type, has type. And this means that type is in type. So the type of type is type. And this is actually, so for example, in other dependently typed languages, this is not used. So for example, in Agda, you would have type, and and the type would have type 1, type 1 would have type 2. So types are indexed, and there is an infinite hierarchy of types, because if you allow type to have type, so have itself as type, then that allows you to write some kind of paradoxical problems that are non-terminating, and you don't want that to happen in a dependently typed language, because you want all programs to be total, because you want to prove things, and your programs will be proofs, so you want your proofs to be total. But this is not the case in Haskell, because we don't really want to prove anything, because Haskell is already full of loopholes and possibilities for non-terminating programs. So you can just write let x equal x, and then you create the type of x, and x is basically the universal program, because any type, so x can be a value of any type. But of course, x is non-terminating. So if we only want to write programs, then type in type is not a big problem in Haskell, because we already have non-termination, and we don't ruin anything that wasn't already ruined. So this is an extremely nice diagram. We have terms, types, and it's types all the way up or down, depending on how you draw your diagram. Yes, and we also have so if we enable type in type, then we should really import data.kind, because data.kind has type exported, and type is a synonym for star, and it's a bit more readable, although a bit more verbose. So what can we do now? For example, we can have kind synonyms. So this is the kind of monad transformers, and we can create a kind synonym for it. So we don't have to write it out in its glory whenever we want to annotate kinds. And this net definition is only needed for further demonstrations, but we can also have a kind family. For this type family, arity takes a type and computes the arity of the type if it's so basically if the type is an arrow, then this is so this natural number is either 0 or a successor of a natural number, so it's a unary natural number representation. Is basically the one that we use most often in type level programming, because it is the simplest. So we can compute the arity of any type. If it's an arrow, then it's a successor of arity of B. If it's not an arrow, then of course the arity is 0. And for example, we can evaluate the arity of the function type from int to int, and then it is the successor of 0, which is 1. And we can also evaluate the arity of int, which is 0, but, and here comes the spin, we can also evaluate the arity of this type constructor, which is also 1. So this type family works on the kind things, so not just on types, but also on type constructors. And because types and kinds are now the same, we can have, for example, this data definition, which has a type parameter and has another parameter x, which has the kind t. So t is a type, but here we use t as a kind. And then it's just basically some kind of proxy thing that doesn't have any actual content. And for example, this is an example. So polyproxy gets star as the first parameter, and because this is star, this has to be in star. and it is in star. And this is another example. We pass star to star as the first parameter, and then this has to be a type constructor because this has to be in this. And we can also have kind equality constraints. This does not occur very frequently, but it's also pretty funny. So we can have a kind equality constraint as an equality constraint.
A question. So
okay.
0 is just an example term you used for showing this kind, right?
0.
Yes.
So 0 in.
No. In the kind equality constraint example, your last example. So 0 has nothing to do with the actual equality.
Yeah. Of course it has, because this is just an int constraint by an obviously true kind equality constraint. So because this is int, then we put in here 0. But if I put something obviously false here, then this would not type check. Okay. Because that's how the equality constraints in GHC work, and that has not changed. So, and we can also have explicit for us now in data definition. This sum is basically the type. It's an existential wrapper for any type constructors that go from kind A to star. So sum takes an implicit parameter, which is a type, and takes a type constructor, which as input takes an A. So as an input takes something which is in that type, but it's used as kind here. So it can be pretty confusing that types and kinds are now the same, so they can be used in either type context or kind context. So if I bind A as a type, then I can use it either in kind context, or I can use it in type context. So I could mention A in the definition, and then it would be in type context, but it would be the same A. And in kind context, it refers to the lifted kind, and in type context, it refers to just the type. So there is no difference between kinds and types now. So they can be used, exchanged freely, but of course, they would still mean different things in kind context or in type context. Because if you use something in type context, then that would be present in your actual program in runtime. So that would have a value that is present at runtime. But if you use something in kind context, that's only present at the type level. Please ask if anything is unclear. So I suppose that everyone is at least has a basic familiarity with data kinds. Is that true? So anyone who is not familiar with data kinds or lifted kinds? Because I can give a very, very short example. Oh?
I'm a beginner of language.
So sorry?
I'm a beginner of the Haskell language.
Then
it's okay.
Okay, then probably data kinds would be still pretty unhelpful to explain. Okay, so I'm going to go. So basically, this sum is just an existential wrapper around some f type constructor, and we have an x which is an existentially quantified type, and we have an fx, then we have some f, and x does not appear here, so it's a hidden x. It's an existentially quantified x. And we can also have now kind indexed generalized ADTs. So previously we had the normal GADTs, and the normal GADTs are interesting because if you pattern match in a constructor of a GADT, then the type of the actual constructor is refined to whatever type appears in the return type of the GADT constructor. So, and this is another thing that I suppose that everyone is already familiar with. So normal GADTs. But previously, even so, no matter how hard we tried, we could not write a GADT that is GADT-like in kind parameters. But now we can. For example, we can write is G, which takes a type or kind parameter, and an X, which is in that type. And this G int says that our X is actually an int. So if we pattern match on G int, then if we previously had in the context GTX, then if we pattern match on G int, that for example, so if you pattern match on G int, then we will know, and the types are going to be refined in the context. So T is going to be star. This is some kind of pseudo-mathematical notation for assignment. So if you pattern match on a GTX and you find out that it's G int, then T is going to be refined to star, and X is going to be refined to int. And if you pattern match on a G maybe, then T is going to be refined to a star to star type constructor, and X is going to be refined to maybe, and maybe is a type constructor, maybe itself, not the type. So basically now we can also talk about kind equalities in GADTs. And we can also write kind classes. I'm probably not going to go into details here, but if you've done any programming before with singletons, this sync type class is really a big improvement over the previous singleton definitions, because this is a kind class which has a type parameter, and then we can use T in kind context here in an associated data definition, but we can also use it as a type here in a function definition, and also use as a type here in another function definition. And but there are much simpler examples. For example, class foo x star, and then instance foo star. I hope this works. Yes. And instance foo star to star. So this also works. So foo is a kind class because these are kinds in the instance sense. But it could also be used as a type class at the same time. So type in type basically does two things. Why did I write 2 here? So it strengthens the type level. Yeah, because I already wrote one. I'm going to go back a little bit. Yes, so this was the... Okay. So one thing that type in type did was to unify the type and the kinds into just a single level, and so that's basically the kinds got upgraded to the same power of expressivity as types. But type in type also does something else, makes most gadgets or GADTs liftable. So liftable as lifting in data kinds. So previously, if we had a definition like data net, which we already have, equals 0 or a successor of a net, if we enable data kinds, then we also had net as a kind, and z and successor of net as inhabitants of that kind on the type level. But GADTs couldn't be lifted. But now GADTs can be lifted too. So for example, we can have the usual definition of equality, and so the usual definition of equality as it is in dependent type theory and dependently typed languages. So this is a GADT, and it says that if we have any type and we have two elements of the type, then we have the type which expresses the equality of the two elements, and we can give an element of this type by REFL, which is short for reflexivity. So we can only construct REFL if in the program context it is clear that the two indices of this GADT are equal. For example, if I say that P1 has type true equals true, and then P1 equals REFL, then it's fine. I can give REFL as an element of this type because true equals true. But if this is true equals false, then I am going to get a type error because the expected type is true equals false, but REFL only constructs the reflexive relation. And so already before GHC 8, we could do this. We could do this REFL definition, but we couldn't use this equality definition on the type level, and now we can. So we can write a type family. For example, so this is basically we use the type of expressing equality at the type level, and we write a type family which expresses that all type constructors are congruent relative to that equality that we just defined. And I think I shouldn't really explain it any further. And we can also prove that that kind of equality is also symmetric. And so anyone familiar with dependently typed programming can see that now in GHC 8 we have something of a full dependent programming language on the type level and up. Yes?
There is an error in the definition of C.
There's an error? Yes, because yes. No, it's okay. So Sim says that if x equals y, then we can also prove that y equals x. So equality is symmetric as a relation. And other example, for example, we can have the length index vectors. So these are the lists that are exactly this long. And so in previous GHC versions, we were able to define this type and also program with it. But now we can also use this thing at the type level. So we have a type-safe type level head for type level vectors. And we can write a type family head which takes a vector as an input, which is a successor of n length. So it's not empty because its length is a successor of some natural number. It can be 0. So if it's not empty, then we can always take the head element. So it's type safe, and we pattern match on the vector, and we get the head element. And So now we have type-safe type-level programming. And if we say that give me the head of this type-level vector, then we get int. But if I say, please give me the head of the empty type-level vector, that's a type-level type error. So it's pretty nice. And we can also have, of course, concatenation. So we can take two type-level vectors with length n and m, and if we concatenate them together, then the length will be n plus m. And we can do the usual GADT shenanigans at the type level now. However, we still don't have any let or case or any lambda on the type level, and primitive types can be lifted, it's a pretty bad limitation, because string is just a list of characters, but a character is just a pointer to a primitive character hash. So there is a module called GHC.prim, which contains all the primitive functions and the primitive data definitions, and actually internally a character is implemented as a pointer to a primitive character object. So basically it's not possible, because you cannot lift to the type level primitive types. You can't lift anything that contains any primitive type. So you can't lift string, you can't lift int, you can't lift word. Instead, what we have is GHC type literals on the type level, but it's basically it's a hot mess. So it's a very ad hoc solution, because it's basically because we can't have strings on the type levels, we create. So GHC typelets creates a new ad hoc string-like thing on the type level, which is called symbol. And because we can't have ints on the type level, GHC typelets exports a very ad hoc integer-like thing on the type level called net. And most of the time we want string on the term level and the type level to be related, and we want int on the term level and the type level to be related in a straightforward way, but now they are not, because on the term level we have the normal strings or byte strings or text or whatever, and on the type level we have an ad hoc re-implemented different thing that acts like a string but is not, and an ad hoc type level integer-like thing that acts like an integer but it's actually not, and we have different primitives for the type level things and the term level things.
Is there a trend to fix this?
I think no. I have seen a GHC fork with the type level strings, which are called symbols. So the type level strings implemented as actual term level strings. So I've seen a GHC fork, but I don't think that will be merged. So I don't think there are any plans to do this. But on the longer term, if we really want to simplify this whole lifting stuff, so when we get dependent Haskell, then we will have to have the same things on the term and the type level, because we are going to have actual binders, actual pi binders. And at least at that point, this should be fixed.
Do you have a time scale for that?
So Richard Eisenberg is the person who implemented typing type, and is also the person who works on dependent Haskell. And recently he posted on his blog the time frame, and I think that it's going to be GHC 8.6 at the earliest. So because GHC 8.2 will be bug fixes, GHC 8.4 will be Richard being busy with other things, and then GHC 8.6 will be dependent Haskell. So it's quite a few years down the line. And of course, classes and constraints can be lifted, and type family evaluation is very slow. for example, so when I tried to push this thing as far as I could, I basically implemented the type-safe simply typed lambda calculus and its interpreter on the type level with type families. So I'm not really going to talk about it. So GHC Haskell does not have lambdas on the type level, but with GHC 8 you can implement them as an embedded language on the type level with the interpreter on the type level as type families. And so I'm not going to talk about it, but if you implement type lambdas from the scratch this way, and for example, if you try to evaluate simple things like add 2 to 2 or multiply 2 to 2, then it's going to go through all the type family evaluation mechanism in order to actually evaluate it, and it's incredibly slow. For example, if you want to evaluate the multiplication of the unary 2 by unary 2, then it will take about 10 seconds to type check. So, there is a lot of room for improvement, and the way it's actually done in production strength dependently typed systems. For example, in car, you have a very optimized bytecode interpreter for evaluating things on the type level, which is basically just as fast as GHCI. And you can even go beyond that. For example, you can have a just-in-type compiler that takes, for example, type family definitions and compiles them to machine code, and then when you type check your program, you run the machine code in order to get to pull out the evaluated type family expressions, and it's going to be, of course, even faster. So the current GHC implementation of evaluation and reduction on the type level is very far from what's possible or what's standard in Coq or Agda or other dependently typed systems. So, and how it's useful, and so I'm going to say that for most cases it's not useful at all in production context, because because for most business cases you don't need this, and mostly useful as a first step toward more dependent Haskell. So this really has to be implemented if you want dependent Haskell, and it gives us more power for singletons and generics, but it doesn't really say anything to you if you haven't used singletons or generics before. But if you use singletons before, then you are going to be really happy. So if you already did a lot of type level programming stuff, then it's going to make you quite happy. And what's the time? What's the time? The time is almost over.
Maybe it's useful if you use a library which is.
Mm-hmm. Yeah. Yes.
Can you repeat it so recording gets it? Repeat the question.
Repeat. Okay. So the question is, so maybe it's useful as something that in the internals of some library, and then you only get some kind of API out of it that is more elegant or more flexible. And of course, yes. And in general, that's a very large part of the practical benefit of dependent types. So dependent types require an amount of mathematical ability and some kind of theorem proving ability to write well. But if you're a writer of libraries, then you can simply internally do all your proofs and all your complicated abstract mathematical stuff, but you can also present an API that is very clean but very powerful. So, for example, you can have a numerical library for manipulating matrices, which can track all the dimensions of a matrix, and also the sizes of each of the dimensions, and also would prove safe indexing and take the slices and prove that if you index into a slice, it's also safe and things like that. And also, for example, some kind of programming library, much like Servant. So basically, Servant does this already. So Servant is a library that uses techniques from dependently typed programming to present an interface that is very flexible and very powerful. And if you have real dependent types, then you can do things like Servant, but also even more powerful. So Servant is basically just the tip of the iceberg. And I think that the time is over now.
Okay, thank you. Does somebody have any other questions?
Are there any interesting features in GHC 8, or is that all?
So the question is this all of the interesting features?
The GHC brings to
No, I prepared also other things. So we also have explicit type applications, which are very nice and also enable some use cases that weren't really possible or weren't convenient before. And we also have overloaded labels. So overloaded labels is basically so treating type level symbols, so type level strings, as things that can be overloaded. And then if you write something like hash symbol, hash foo inside your program, so something prefixed by hash, then GHC will treat this foo as a type level string, and you can overload it because there is a type class for overloading this kind of expression. And it basically gives you a basic but pretty nice mechanism for overloading record fields or lenses based on record fields. And there are also a bunch of other features which I didn't even prepare for. For example, there are custom compile time errors. So you can write instances for a class, which when GHC resolves that instance, it instead generating code, it generates a type error, and then inside the class you can specify what kind of error message you want to throw. So it's also pretty nice. And we also have Strict Haskell, which is a pragma, and if you put Strict Haskell as a language pragma on top of your file, then everything is going to be strict, all definitions and all functions strict by default. And you also have stack traces and exceptions with locations, source locations, so and other things. But I'm not going to.
Are there any libraries or projects which you know of which use these features, and one could look at it and learn, for example, the patterns of usage of dependent types or these features which you described?
Well, so you can look at Servant, and because it's popular and you can see why it's useful, but it's not the purest expression of dependently typed programming, because it's very pragmatic, and dependently typed programming with GHC is very ugly. And if you want to do so something that's closest to the real thing in GHC, then you can look at the singletons library and the documentation for the singletons library, or just search for Stack Overflow of questions and answers, of which I've written a lot with singletons. And but really the best way is to install Agda and install Agda and learn Agda, and then wait 5 years and then go back to GHC.
Because my problem is that, okay, I see all these features, but I like the experience how exactly to use it in a practical way. So, because, for example, in the dependent type world, all the tutorials, all the descriptions just show S and Z and then vectors, and that's about it. So, and it would be also good to see other examples how you could use it, what are the tricks, or
So I'm afraid that that kind of material and documentation does not really exist. So basically, I think the cleanest way is to get Agda and get, for example, Patty has written a nice Agda tutorial, and then you can go through that, and you can think about how that could be applied to practical problems. And so basically, maybe less than 1% of all the practical possibilities and all the opportunities have been even considered. And so, for example, in any business case, you just pretend that you have you can pretend that you have dependent types, and you can come up with some fancy abstraction that's pretty nice in 5 minutes. But the problem is you don't have dependent types.
So I just have a note to your question, for the previous question. For the practicalities and dependent types, imagine dependent type systems as the lack of ability we actually don't have right now in Haskell. And for searching for real world things, it's easy. Like you write some Python code which can be typed with Haskell, but still has some meaning. And that's the example you are looking for. Where should you use dependent types?
Yeah, yes. That's an interesting technique. So you can take some kind of really complicated untyped code, which you can't really type in Haskell, but you can type independently typed languages, because a lot more. So you can express more programs in independently typed language, and it's a pretty nice exercise. So you take something that's untyped and complicated and try to come up with types for them. And it's also a nice exercise because if you succeed, then you will understand your original untyped program much better, because now you have some kind of formal perspective.
So, thank you. So now we'll have the 3 lightning talks. So if one register to it, please come here and we'll have it.
How much time do you need for?
I can represent it in 5 minutes or 15 minutes. They're all programming in Haskell, so we can encode all. And if nobody interested in that, I'm just skip it. Or just few.
I think this would be interesting. Do you have slides or?
I have some code to show. I just need to grab my laptop.
Did I access to the snippets of codes you
Yes, of course.
all folders?
So the organizer